Hello, in our previous lesson, we defined trigonometric functions using right triangles, which limited us to working with acute angles between 0 and 90 degrees. In this lesson, we're going to extend those ideas so that trigonometric functions apply to any angle, including angles larger than 360 degrees, and even negative angles. This is an important step because it allows us to use trigonometry to describe full rotations and real-world motion. Let's get started. In this section, we will learn how to define all 6 trigonometric functions using coordinates in the plane. We will determine the sign of each function in each quadrant, evaluate trig functions at key angles on the axes, and use reference angles to compute exact values. We will also use Pythagorean identity to find missing values. The key idea throughout this lesson is that we are moving beyond triangles to a framework that works for every angle. Right triangles are very useful, but they only allow us to work with angles between 0 and 90 degrees. However, many real-world situations involve motion that goes beyond that. Objects rotate, spin, and even move backward. So the question becomes, how do we define trigonometric functions for any angle, not just acute ones? The solution is to move from triangles to coordinates. Instead of relying on side lengths, we describe an angle using a point, xy, on its terminal side. This approach works for all angles, positive, negative, and beyond one full rotation. Let's begin. Let theta be any angle in a standard position, and let xy be a point on its terminal side. We then define r to be equal to the square root of x squared plus y squared, which represents the distance from the origin to the point. Using this, we define the trigonometric functions as follows. Sine theta is equal to y over r, cosine theta is x over r, and tan theta is y over x. The remaining functions are their reciprocals. A very important observation here is that r is always positive because it represents a distance. That means the sign of each trig function depends only on the signs of x and y. Also notice that sine and cosine are defined for all angles, while tangent and secant require x not equal to 0, and cotangent and cosecant require y not equal to 0. Let's do an example. Suppose the terminal side of an angle passes through the point 5, negative 12. We begin by finding r. r is equal to the square root of 5 squared plus negative 12 squared, which is equal to the square root of 169, which is equal to 13. We now evaluate the trig functions. Sine of theta is equal to negative 12 over 13, cosine theta is equal to 5 over 13, and tan of theta is equal to negative 12 over 5. The remaining functions follow as reciprocals. Now let's check the quadrant. Since x is positive and y is negative, the point lies in quadrant 4. This confirms our signs. Cosine is positive, while sine and tangent are negative. Because r is always positive, the signs of the trigonometric functions depend entirely on the signs of x and y. In quadrant 1, both x and y are positive, so all trig functions are positive. In quadrant 2, x is negative and y is positive, so sine is positive. In quadrant 3, both x and y are negative, so tangent is positive. In quadrant 4, x is positive and y is negative, so cosine is positive. A helpful way to remember this pattern is all students take calculus. Now let's work with partial information. Suppose we are given sine of theta is equal to negative 2 over 3, and tan of theta is greater than 0. We begin by first identifying the quadrant. Since sine is negative, y is less than 0, which places us in quadrant 3 or 4. Since tan is positive, y over x is greater than 0, which means x and y have the same sign. Because y is negative, x must also be negative, so the angle lies in quadrant 3. Now we assign values. Y is equal to negative 2, and r is equal to 3. We then use the Pythagorean relationship x squared is equal to r squared minus y squared, which is equal to 9 minus 4, which is equal to 5. So x is equal to negative square root of 5. Now we compute. Cosine theta is negative square root of 5 over 3. Cosecant theta is negative 3 over 2. And cotangent theta is equal to square root of 5 over 2. At certain angles, the terminal side lies directly on one of the axes. For example, at 0, the point is 1, 0. At pi over 2, the point is 0, 1. At pi, the point is negative 1, 0. And at 3 pi over 2, the point is 0, negative 1. When evaluating trig functions at these angles, we must be careful about division by 0. For example, tangent is undefined when x is 0, and cosecant is undefined when y is equal to 0. Let's evaluate some key values. Cosine of pi is equal to negative 1. Sine of 3 pi over 2 is equal to negative 1. And tan of pi is equal to 0. And secant in pi over 2 is undefined because x is 0. These values come directly from the coordinates of the points on the axes. A reference angle is the acute angle formed between the terminal side of an angle and the x-axis. Reference angles are always between 0 and 90 degrees. They allow us to use familiar values from special triangles to evaluate trig functions for larger or more complex angles. The process is simple. First, find the reference angle, then evaluate the trig function using known values, and finally apply the correct sign based on the quadrant. Let's look at a few examples. For 7 pi over 6, the angle lies in quadrant 3. The reference angle is 7 pi over 6 minus pi, which is equal to pi over 6. For 315, the angle lies in quadrant 4, and the reference angle is 360 minus 315, which is equal to 45. For a negative angle, like negative 11 pi over 4, we first find a coterminal angle by adding 2 pi. Negative 11 pi over 4 plus 2 pi is equal to 5 pi over 4. Then 5 pi over 4 minus pi is equal to pi over 4. These are the key values you should know for 30 degrees, 45 degrees, and 60 degrees. The sine values follow a clear pattern: 1/2, square root of 2 over 2, and square root of 3 over 2. The cosine values follow the same pattern, but in reverse order. These values, combined with reference angles and quadrant signs, allow you to evaluate many trig functions without a calculator. Let's evaluate a few examples. Cosine of 7 pi over 4 is equal to square root of 2 over 2. Sine of negative 150 degrees is equal to negative 1/2. And tan of 5 pi over 3 is equal to negative square root of 3. The process is always the same. First, find a coterminal angle if needed, determine the quadrant, find the reference angle, and then apply the correct sign. Let's apply these ideas. The reference angle for 240 is 60. Sine of 240 is equal to negative square root of 3 over 2. And cosine of 5 pi over 6 is equal to negative square root of 3 over 2. And if cosecant is positive while tangent is negative, the angle must lie in quadrant 2. Now let's use a Pythagorean theorem, the Pythagorean identity, to fill in some gaps. Suppose cosine of theta is equal to negative 3 over 7. And the angle lies in quadrant 3. Using the identity sine squared theta plus cosine squared theta is equal to 1, we find that sine theta is equal to negative 2 times square root of 10 over 7. Then tan of theta is equal to 2 times square root of 10 over 3. The signs follow from the quadrant. Let's put it all together. Suppose tan theta is equal to 3 over 4 and sine of theta is less than 0. This places us in quadrant 3. Let x equal negative 4 and y equal negative 3. Then r is equal to 5. So the sig trig functions are as follows. Sine of theta is negative 3 over 5, cosine theta negative 4 over 5, tan theta 3 over 4, and the reciprocal functions follow from these. To summarize, we extend trigonometric functions to all angles using the x, y, r framework. The signs of trig functions depend on the quadrant. Reference angles allow us to evaluate functions using familiar values, and the Pythagorean identity allows us to find missing information. These ideas form the foundation for understanding trigonometric functions on the unit circle and their graphs.